So, hello to all of you. I'm obviously not here, so I'm recording this on Friday, and I'm going to tell you a little bit about chemical equilibrium. Oh, Mr. Ing, feel free to pause this or whatever is necessary or chime in. So, chemical equilibrium is a very odd thing, although it's prevalent everywhere, so it's mildly important to understand it. It's actually something that affects all of our lives, whether we really think about it or not, and we've actually had balance or experience with this. So what we're going to try and figure out is how do we establish a chemical equilibrium? It's actually not that difficult of a task. So the first things that we need to review, hopefully you can see the mouse, is that reaction rates actually exist. And when we deal with a chemical reaction, what we're looking for is how quickly we're losing reactants. So what I should notice over time is that the concentration of my reagents or my reactants is going to decrease. That's nothing that should be a big whoop-de-doo. And if we're losing reactants over time, what I should actually see is also a buildup of products over time. So in reality, if I'm measuring reaction rates, I can either look for how quickly my reagents or my reactants disappear, or I can look for how quickly I'm producing products. Either one, I can create a reaction rate. Those units are going to be in molarity per second, which is either written big M/S, or big M with an S to a -1 power. Either one means molarity per second. There's lots of things we could do to influence it, like changing the temperature or the concentration, or adding a catalyst, or blah, blah, blah. We've dealt with that before. You have a quiz on this on Friday. One of the things that we can do is we can actually create a mathematical statement to describe this. This reaction rate we can write in the form of a law, which means I can mathematically express what's going on when it comes to the reaction rate. We're not going to write rate laws. If you take AP chemistry, you'll learn how to write rate laws. Here, we don't necessarily care about that. We just care that we can determine a reaction rate. This is important because in part I've been lying to you, and I pointed out that I was lying to you last week. That is, some reactions go backwards. So if you recall, and I didn't put in an energy diagram, so maybe Mr. Ing will write down an energy diagram, or maybe you can write your own. If we have some reactants turning into products, so A plus B turns into C and D, there'll be some type of energy of activation for this, and there will be a reversible energy of activation, meaning going from products to the peak back down to reactants. When I look at this, every once in a while, if that reversible energy or activation energy is a tad too big, what I might not let happen is this reaction go backwards, meaning the barrier to go backwards, meaning products to reactants, might be too large, and the result is you turn reactants only into products. There are other cases where if that activation energy in either direction is kind of small, what you might get are two different reactions going on at the exact same time, meaning A plus B might turn into C and D, but you also could have C plus D turning into A plus B, because if the activation energy is small in either direction, it's possible to have this reaction under a certain set of conditions go backwards. That happens, we say we have a reversible reaction. There are actually several examples of this. What we have here is a simple example of something that's reversible or not. That is and this isn't even real chemistry, this is just adding waters or not. And this is called copper sulfate. Copper sulfate is a nice blue color, and it's blue in part because it has water on it. So this would actually be called copper 2 sulfate pentahydrate. We'll just call it copper sulfate with water attached. If I were to stick it into an environment where I'm shoving energy in to the crystals, meaning I'm heating it up, what will happen is the water will be driven off and I'm left with anhydrous, without water, copper sulfate. But in any environment where I can put them, there's going to be some water, and that some water might come back and reattach itself onto the copper sulfate to go backwards and form our blue hydrated copper sulfate. So we get a balancing act. Sometimes we can turn the blue copper sulfate into the white version, and sometimes we turn the white version back into the blue version. You reach a balancing point that in any set of conditions, when the reaction is reversible, where we kind of have a standoff, meaning it doesn't seem to get any bluer, but it's also not getting any whiter. It just kind of is stuck where it's at. And we call that a chemical equilibrium. What we look at when we think of a chemical equilibrium are two rates of reaction, what we call the forward rate and the reverse rate. I'm turning reactants into product, we call that the forward rate. I'm turning products into reactants, I call that the reverse rate. At a chemical equilibrium, the two rates are the same, meaning I am turning reactants into products just as quickly as I'm turning products back into reactants. It's like if you had a room with two rooms with toys, and if you pick up one toy from one room to bring it into the other, but at the exact same time someone is grabbing a toy from the other room to bring it into the first room, no matter how many times you do this, if you keep moving one toy at a time at the exact same speed, we're always going to keep the same number of toys in the rooms. No matter what, we just kind of have a standstill. Is stuff happening? Absolutely. You're still moving presents back and forth. The catch is, if you just looked at the presence there, you wouldn't notice a difference. That is what we call the equilibrium. So if we were to try and put this in terms of an analogy, we could have a mountain, or at least three mountains. First mountain will have a whole bunch of skiers on the bottom. Don't they look happy? Clearly they haven't paid for their ski tickets left yet. So what I'm going to do is take some of these and I'm going to start to move them up the mountain. So I'll have two of them and they'll move on up the mountain. Good for them. They moved on up. Once they're at the top, some more might want to come back, might want to go up too. So I might get some more going up. The catch is there's only so much space at the top, so I'm also going to get some moving down. And what the result will be is we're going to have a standoff of so many at the top, so many at the bottom, because if we have two go up, two have to come back down. We have reached an equilibrium where the population of one side seems to be holding steady, the population of the other side seems to be holding steady. Are things changing? Yes, individuals are moving up and down the mountain. If all we're looking at are the numbers of people, do we notice a change? The answer is no. We can't tell that anything is happening. If we look, we can notice there are things going on. But in the big picture of how many are at the top, how many are at the bottom, the answer is always the same. Nothing is changing. So, like I made reference to, equilibrium exists in a whole lot of places. This here is just a little list of some of the places where you can actually find chemical equilibrium. Some of them are biology, some of them are chemistry, some of them are you going to a mall, some of them have to do with economics, some of them have to do with puddles of water or how you're behaving with your parents. As long as you have a balancing act where you don't really notice anything changing, that's an equilibrium. Things are occurring between the two sides, between reactants and products, or water vapor, or liquid water, or you and your parents, or supply and demand. There's still something going on. There's still interaction. But when we look at it from far away, it looks like nothing's happening at all. It's not true. Stuff is happening, but it just looks like nothing is happening. The way that we show that equilibrium is happening is with a constant. And we call this constant K, because K just turns out to mean any type of constant. I yawned. Hopefully you all aren't yawning now too. So we have some type of constant that's happening. The equilibrium constant turns out to be a ratio, and it's a ratio of reactants and products. In particular, it's a ratio of the products over the reactants. So products over reactants. That's what we put in terms of order. It's the end over the start. When I get my number, if K is greater than 1, what we say is they're at equilibrium, the top is heavier than the bottom, meaning I have more products at equilibrium than I have reactants. If it's the opposite, K is under 1, so it's like 0.1 or 0.001 or something like that. Not negative, you don't get to go negative, but somewhere between 0 and 1, we say that at equilibrium, the reactants are top heavy and you don't have or bottom heavy and you don't have as many products. So equilibrium is kind of a nice, or the equilibrium constant is a nice way to kind of say, here's where the equilibrium is. Is it right if you get an equilibrium of 1, that'd just be the products equal the reactants. The top and the bottom are the exact same. So if I can get a scale, I can tell you where the equilibrium turns out to be. The bigger the equilibrium constant is, the further it is on the product side. The smaller it is, the more it's on the reactant side. If it equals 1, we're ram smack in the middle. When we write this equation, what we happen to use are these little brackets. The brackets mean concentration, so how much stuff in space. We would call that molarity, moles per liter. So we look at the concentration of C at equilibrium, the concentration of D at equilibrium, as well as for A and B at equilibrium. We have exponents. Those exponents are coefficients. It's the numbers that we would write in front of whatever the chemical or compound turns out to be. So if A turned out to be 1, B is 2, C is 3, D is 4, this would be C to the 3rd, D to the 4th, A to the 1st, or just A, and then B squared. That's what we would end up writing to figure out our equilibrium constant. C has to do with concentration, or the amount of stuff, which means that has to be able to vary. It turns out gases and aqueous solutions can vary, but if you have a liquid or a solid, I can't actually write that into here because the concentration of a solid is the solid. The concentration of a liquid is whatever the liquid is. So that can't change. So all we can put into this are gases or aqueous solutions. So let's try an example. So it shows you everything all at once, but we can walk through it. I meant to animate it, and oops, I didn't, and I'm not re-recording this. So when you write out a KEQ statement, there are 2 things that you need to do. First thing you have to do is make sure it's balanced. If it's not balanced, whatever you write, you're wrong. The second thing is you then write the equilibrium statement. But step number 1, you have to make sure it's balanced. If it's not balanced, you are wrong every single time. So the example would be hydrochloric acid plus aluminum hydroxide is in equilibrium with water and aluminum chloride. Step number 1, I need to balance it. So when I go through and balance, I realize, oh, I need 3 chlorine, so I'll stick a 3 in front of that H. That gives me 3 H's, that's 3 OH's, so I need to have 3 waters, so I put a 3 over there. I have 1 aluminum, everything's balanced. So I just need 3, 1, 1, 3, balanced. Next step is to write my equilibrium equation, my KEQ statement. It's products over reactants. So I have aluminum chloride, the concentration of aluminum chloride, multiplied by concentration of the water over the concentration of hydrochloric acid, as well as the aluminum hydroxide. The catch is water is a liquid. Liquids we can't write a concentration for because they're just water. It's just a liquid. Water is water is water. So when I write my KEQ statement, all I can list at the top would be my aluminum chloride. The aluminum chloride will be over these 2 things multiplying by each other. The concentration of hydrochloric acid to the 3rd power, because there's a 3 in front, multiplied by the concentration of my aluminum hydroxide, which is just to the 1st power because there's a 1 in front. We just don't write the 1. So your task right now with Mr. Ng is see if you can do these problems. See if you can write down KEQ statements. Step number 1, make sure they're balanced. Step number 2, make sure that you can write the equation, products over reactants. Coefficients show up, so it matters if you balance it correctly.